Welcome to The Explainer. Today, we're unpacking a really mind-bending biological puzzle. The sheer mystery of animal lifespans and why they vary so wildly across the animal kingdom. Nature is packed with incredible secrets, but honestly, the way it hands out time to different creatures, it's probably one of the most fascinating things out there. We've got some great visuals to help guide us through the data today, so let's just jump right in.
Right off the bat, I want you to look at this biological contrast. We're dealing with two extremes that literally sound impossible. On one side, you have the mayfly. This is an insect whose entire adult life is measured in just a few hours. And then, on the exact opposite end of the spectrum, you've got the massive Greenland shark, a creature that silently patrols the icy, freezing ocean depths for centuries. So how is it that two living beings sharing the exact same planet and the same basic biological building blocks can experience time on such radically different scales?
Okay, let's dive into this. Section 1, the extremes of life. To really grasp the sheer scope of this mystery, let's look a little closer at the adult mayfly. Get this, it actually emerges without a functioning mouth. It literally never eats. It exists purely to reproduce, and then it dies just a few hours later. It's wild.
Which naturally leads us to our main question today. What actually causes such enormous differences in lifespan? I mean, if biology can figure out how to sustain a shark for hundreds of years, why wouldn't it do the exact same thing for the mayfly? To figure this out, we kind of need to put on our detective hats and challenge some of the everyday assumptions we make about the natural world.
And that brings us to Section 2, the body size myth. If you ask most people, they'll probably tell you that bigger animals just automatically live longer. And, when you compare a massive elephant to a tiny little house mouse, that assumption seems completely spot on. But biologically speaking, it is a massive red herring. And this brilliantly illustrates exactly why body size isn't the full story. Let's walk through these rule breakers. Sure, at the top, the mouse and the elephant are perfectly following that bigger equals longer rule. But look right underneath that. You've got parrots, birds you can literally hold on your forearm that can easily live for over 80 years. Then there are giant tortoises blowing right past the 150-year mark. And then the absolute champion, the Greenland shark, hanging around for close to 400 years. If body size really dictated everything, this data would look completely different. So if size isn't pulling the strings, what is?
Moving right along to Section 3, the evolutionary survival strategy. To really understand lifespan, we actually have to look at the daily pressures an animal faces. I want you to try something. Literally imagine yourself as a wild rabbit, just surrounded by predators.
As that rabbit, you are under incredibly high threat all the time. So your best survival strategy is definitely not to build a durable body meant to last 100 years. You wouldn't survive long enough to use those years anyway. Instead, your strategy is all about living fast. You grow up quickly, reproduce as early as possible, and leave behind as many offspring as you can before your luck inevitably runs out. Now, flip that and look at the giant tortoise. Protected by this massive, impenetrable shell, you suddenly have almost no natural predators. You can safely wander the earth for decades under very low threat. In that specific situation, living longer makes total sense because it gives you decades of extra chances to reproduce. So here is the absolutely crucial takeaway. Evolution only rewards longevity when it fits the survival strategy. Evolution is intensely, ruthlessly practical. It doesn't just hand out long lives for free, because building a body that can last for centuries, that takes a massive amount of biological resources. Living longer only makes sense and is only rewarded by evolution if your environment actually allows you to survive safely enough to use those extra years. All right, Section 4, metabolism and life speed. Now we're going to pop the hood and look at the biological mechanics, specifically metabolism, which is literally the speed at which an animal lives its life. Let's compare the internal engine of that mouse with the tortoise. Animals with fast metabolisms, like mice, burn through energy incredibly fast. I mean, a mouse's heart can beat hundreds of times in a single minute. They are basically biological sports cars, constantly running at the red line. Tortoises, on the other hand, live much, much slower lives. We're talking vastly slower heart rates and extremely low energy use. And what we find across so much of the animal kingdom is that a slower internal lifestyle is tightly linked to a much longer overall lifespan. Now, what's really interesting about this slide is just the sheer scale of what living slow can actually mean. Look at this number 100. This brings us back to the Greenland shark.
These guys grow so unbelievably slowly in those freezing Arctic depths that some individuals don't even reach adulthood until they are over 100 years old. Just let that sink in. Imagine spending an entire century just in your childhood.
And because their biological clocks tick at that insanely slow pace, scientists estimate that the oldest Greenland sharks may live close to 400 years. 400! Just think about all the human history that has come and gone while a single shark has just been quietly swimming in the dark. It's absolutely staggering, and it makes them the longest living vertebrates ever discovered by science.
Which brings us to Section 5, the biology of aging, because everything we've talked about so far ultimately dictates how an organism handles the physical wear and tear of simply being alive.
Over the years, biological wear and tear happens inside the body in a few very distinct ways. First, cells just simply wear out. Then, your DNA, the fundamental blueprint of the animal, starts taking damage from environmental factors and normal biological processes. And eventually, tissues just lose their ability to repair themselves effectively. It's the harsh, mechanical reality of aging that eventually stops the clock for every living thing.
But here's the catch. Not all species age at the exact same speed. Our animal rule breakers, like the giant tortoises, the bowhead whales, and those ancient Greenland sharks, are remarkably good at slowing down this cellular damage. Their bodies have literally evolved specialized mechanisms to protect their DNA and keep their cellular repair systems running smoothly for decades or even centuries longer than the rest of us.
So why does studying these rule breakers matter to us, as humans? Well, it's definitely not just abstract trivia. Scientists are studying these specific long-living species incredibly closely right now. Because if we can figure out the exact biological mechanisms they use to resist aging, repair their DNA, and maintain their tissues, that could one day unlock some really profound secrets about our own human lifespan. By studying a tortoise or a shark, we are quite literally searching for the biological keys to human health and longevity.
To wrap up the explainer today, I really want to leave you with this fantastic thought. Some species win by living fast, others win by living long, and both strategies have been successful for millions of years. Nature doesn't have just one single standard for success. It doesn't reward every species with a long life, because honestly, a long life isn't always the best way to survive. Instead, evolution gives each animal exactly the lifespan that best fits its unique way of existing in the world. Whether it's the frantic, fleeting hours of the mayfly or the slow, quiet centuries of the Greenland shark, every creature has exactly the time it needs to play its part. Which leaves us with one final, pretty fascinating question. If nature can engineer a shark to thrive for 4 centuries, what is the true biological limit for us? Thank you so much for joining me today. Keep wondering, keep learning, and I'll catch you in the next explainer.